double integration, moment area, and conjugate beam do not work well for predicting deflections of frames. So in this problem we'll predict both displacement and slope for a frame using virtual work. The key concepts we'll use are selecting the appropriate virtual load for predicting a particular real deflection and generating equations for moment in a frame. And here's our frame. It's determinate with only reactions at point A. Now I will point out we can use the virtual work method to predict displacement and slope in an indeterminate frame. However, the analysis to find the moment equations becomes much more challenging. In this problem, we're going to predict vertical deflection at point C and slope at point C. We'll note that point A is a fixed support and B is a fixed joint. The moment of inertia and the modulus of elasticity are constant for all pieces of the structure. And now our approach. We'll start by approximating our answers. We want to perform an analysis quickly that will give us an estimate of the answer that we can use to compare against our more lengthy calculations later so that we can have some assurance that we have a reasonable prediction. We'll then generate moment equations from the real load. Now in theory, deflection and slope, or displacement and slope, in this frame will be due to both bending and axial deformation. But if you perform the calculations using realistic cross-sectional areas, in a frame the axial deformation typically does not contribute much, and in this frame we will ignore that contribution. So we'll only need the moment equations. We'll need the moment equations from the virtual force. We apply virtual force to predict displacement, and then we'll need moment equations from a virtual moment, which we apply in order to predict slope. Once we have all those equations, we'll be ready to predict displacement and slope. It'll be two independent calculations by virtual work. Then our last step is to compare those with the approximations. Great, let's get started. We'll begin by approximating the answers. So if we draw the elastic curve, we know that the cantilevered end will bend down, but that causes a couple moment at the top here at B, which will cause this one to bend. So we have to be vertical still at point A. But we should get an elastic curve that looks something like that. We'll approximate it as just a cantilever with the uniform distributed load of 0.4 kips per foot. And that cantilever is 8 feet long. The displaced shape in this case will be as such, and so we'll get our approximated displacement as such, and approximated slope as such. Now if we take a look at this displaced shape and see that the base, or the fixed end, is already rotated, we see that this will underestimate our solution. But if we look at the front cover, we can find formulas for these deformations. Under the beam deflection and slope section, if we look on the second page, we find cantilevered, uniformly loaded, the displacement at the end is minus omega L to the fourth over 8 EI. So our approximation, which will be an underestimate, is minus omega L to the fourth over 8 EI, where L is the length of our cantilever. Negative because those equations are based on up as a positive displacement. So we have negative 0.4 kips per feet, 8 feet raised to the fourth power, over 8 EI. Put it all together, we have a prediction of minus 205 kip feet cubed over EI. And it's negative, up would have been positive. To predict slope at that end, we go back to the front cover. The slope at the end is minus omega cubed over 6 EI. Minus omega times L cubed over 6 EI. And this is negative because a positive slope at this end using the formula would be a rise. So we have a minus 0.4 kips per foot, 8 feet cubed over 6 EI, which gives us a negative 34.1 kip feet squared over EI, and a positive quantity would have been clockwise slope. Now we have our predictions, which we know are underestimates. Once we get done with our more lengthy calculations using virtual work, we'll come back and compare them. If they don't match favorably, we'll have to decide whether we've misunderstood something or if we've made a mistake. Now step 2. Let's generate the moment equations from the real load. We will need two axes in order to describe moment everywhere in this frame. Since there are two members, we'll need at least two. We have no concentrated forces or couple moments applied in between the ends of each member. We don't have a distributed load starting or stopping within the ends of the member, so two will be sufficient. And so I'll pick x1 to start at point C, where the moment is 0, and then I will pick x2 to start at B. In order to calculate the moment equation, I'll need to cut it somewhere in the range of x1, and I'll draw a free body diagram of the part cut in the range between C and B, cut it at x1, and I will keep the left piece, which is x1 long, has the uniform distributed load, unknown shear as a function of x1, and unknown moment as a function of x1. I'll then sum moments about the cut. I get to choose which direction to be positive for the summation. I will choose counterclockwise since that's direction of my unknown moment, and it's also the direction that the distributed load causes rotation about the cut. So I multiply the distributed load times x1 to get the force resultant, times x1 over 2 to be the location of the resultant, and we add in the unknown moment as a function of position x1. Solve that, and my equation for moment is minus 0.2 kips per foot x1 squared. Now for our next moment equation, we need to cut it somewhere between A and B. I'll cut it there, we'll say. Draw a free body diagram of the section. Cut in the x2. I'll keep the entire top piece. So it is x2 tall, 8-foot cantilevered arm, uniform distributed load of 0.4 kips per foot. We have unknown shear as a function of x2, and unknown moment as a function of x2. I'll sum moments about the cut. Again, I will choose counterclockwise as positive. Get the contribution from the uniform distributed load, which acts over a length of 8 feet, turns it into the force resultant, at a distance of 8 feet over 2, being the location of the resultant. We add in our unknown moment as a function of x2. Solve that, and my equation for moment is a minus 12.8 foot kips. My equation is actually a constant, which makes sense because there's no shear between A and B, so the moment diagram should be constant. Step 3 is to find the moment equations due to the virtual force. So we'll use these to predict the displacement of C. So to do that, we need to remove our real load and apply our virtual load. We have to apply our virtual load at the location where we want to predict deflection, point C, and we need to apply it in the direction we want to predict deflection, in this case up or down. Since we draw it down, our assumption is that the deflection of the real structure will be down. If we get a positive quantity, then that's our prediction. If we get a negative quantity, then our prediction is that the deflection at C will be up. And in the case of this structure, that'll be a concern that we've made a mistake. So as a reminder, to find displacement of C, we need a virtual force. And as we generate our equations, we have to use exactly the same coordinate system that we used to find the moment equations from the real load. So I'll begin by cutting it in somewhere between C and B, and I'll draw a free body diagram of the section cut between C and B. I'll keep the left piece, which is x1 long, and has the virtual force applied at the left end, unknown shear as a function of x1, and unknown virtual moment as a function of x1. Some moments about the cut. I can choose any direction I want as positive. I will choose counterclockwise as positive because all of the quantities create a positive or counterclockwise rotation about the cut. And then I solve for the virtual moment as a function of x1, and I get a negative x1. Now I'll cut it somewhere between A and B, draw a free body diagram of the top section down to the cut. So this is x2 tall, this is 8 feet wide. We have the virtual force applied, unknown shear as a function of x2, and unknown virtual moment as a function of x2. Let's sum moments about the cut. Cut, there we go. And we'll take counterclockwise as positive, 1 through 8 feet, plus the virtual moment that is a function of x2. Solve, and our virtual moment in the region of x2 is a constant, minus 8 feet. Step 4, we said, is to find the moment equations from application of the virtual moment. And why do we do that? To find the slope at C, we need to apply virtual moment, not a virtual force. So again, we remove the real load and apply a virtual couple moment at C of magnitude 1. And since we think that the slope will be counterclockwise or down at C, then we'll draw a counterclockwise couple moment. If we get a negative answer, it means that the tip slopes upward relative to its original horizontal direction. And based on our predicted elastic curve, that would be a sign we probably made a mistake. So to begin, I cut it somewhere in the region between C and B. Draw a free body of the left piece, length x1, with the couple moment of 1 at the left end, unknown shear, which is a function of x1, and unknown virtual moment, which is a function of x1. Now I've labeled this little m x1, but it does not have to be the same equation that we got in step 3, because this is due to a virtual moment. So just make sure that we keep these separate from the moment equations in step 3. To find it, I will sum moments about the cut. I'll take counterclockwise as positive. We get the contribution of the couple moment and the unknown virtual moment. Solve the virtual moment as a function of x1 and get the constant -1. If we take a look at this structure, there's no shear in member CB, which means the moment must be constant. So now let's cut it somewhere between A and B and draw a free body diagram of the top piece, which is x2 tall, 8 feet wide, has the virtual couple moment at one end, unknown shear as a function of x2, unknown virtual moment as a function of x2, and again I will sum moments about the cut. Counterclockwise is positive. And I have the contribution of the virtual couple moment and the unknown virtual moment. The distance away of the applied couple moment doesn't affect our moment equilibrium equation. And once again, my virtual moment is a constant, -1. Now we're ready to predict displacement and slope. The displacement we're going to predict is delta C, vertical deflection at C. And to do that, we sum integrals over the length of the members, virtual moment times moment due to the real load, integrated over with respect to dx. And so this will equal, for member CB, the integral from 0 to 8 feet. Our virtual moment we found in step 3 to be a minus x1 for the virtual load. And our real moment we found to be minus 0.2 kips per foot x1 squared. x1 squared. Divide that by EI. Integrate with respect to x1. And then, for member BA, we integrate from 0 to 10 feet. Our virtual moment was a constant minus 8 feet. And our real moment was another constant, minus 12.8 foot kips. divide that by EI, integrate with respect to x2. And so I'll get the two negatives cancel, and I'll get a 0.2 x1 cubed. When I integrate that polynomial, it becomes x1 to the fourth divided by 4. So we'll have a 0.2 kips per foot, x1 to the fourth over 4 EI, and we're going to evaluate that from 0 to 8 feet. I'll add to it, again the negatives will cancel, the two constants multiply together to be 102.4 kip feet squared. I integrate a constant and I get x2. The power on x2 is 1, so it's just divided by 1 EI. And we'll integrate from 0 to 10 feet. This becomes 0.2 kips per feet, 8 feet to the fourth over 4 EI minus 0, and we add the 102.4 kip feet squared times 10 feet over EI minus 0, since the 0 goes in for x2. Here we're going to get kip feet cubed over EI. Here we're going to get kip feet cubed over EI. That's good. They need to be consistent units, and that's worth checking when we're integrating polynomials. Together, this combines to a positive 1,229 kip feet cubed over EI. Remember, we drew our virtual force down, so a positive means we have a downward prediction. Now to predict the slope at point C. That is still done by summing the integral over the length of the elements or members, virtual moment times the real moment over EI dx. Now I want to point out the capital M, the moment due to the real loads, didn't change from our prediction of displacement of point C. It's only our virtual moment that changes. We'll start with member CB, so we'll integrate from 0 to 8 feet. The virtual moment in this case is a constant -1, and we'll multiply it by the -0.2 kips per foot x1 squared. So we have the -1, the -0.2 kip per foot x1 squared over EI dx1, to which we add, for member BA, integral from 0 to 10 feet, our virtual moment, for the case where we applied a virtual couple moment, is -1 in the range of x2 as well. And as a reminder, our real moment is a -12.8 foot kips. 12.8 foot kips over EI, integrate with respect to x2. Two negatives cancel, so we get a 0.2 kip per feet. x1 is elevated to the cubed or third power, and therefore we have to divide by 3, and we'll evaluate that from 0 to 8 feet. We'll add to that, the negatives cancel, so we get a positive 12.8 foot kips. That's a constant, so we'll get x2, that's the power of 1, so a 1 EI integrated from 0 to 10 feet. That equals 0.2 kip per foot, 8 feet cubed over 3 EI minus 0, which is evaluating the lower bound of our definite integral. And by the way, remember, in double integration, we had constants of integration because we had indefinite integrals. In virtual work, we have definite integrals, so we have no constants of integration. We have our 12.8 foot kips times the 10 feet over EI minus, we substitute in 0, and that whole term disappears. I put these all together, and we get a plus 162 kip feet squared. Kip feet squared, kip feet squared. Good, so we have consistent units over EI. It's a positive quantity, and we assume downward slope or counterclockwise rotation would be positive. So now we're ready for step 6, where we compare our virtual work results with our approximations. We approximated the vertical displacement at C to be a negative 205 kip foot cubed over EI, where up is positive. And using virtual work, we predicted that it would be a positive 1,229 kip foot cubed over EI, where down is positive. Where down is positive. So when we compare these two, our directions turn out to be the same. Even though they're of different signs, our sign convention changed between the two methods. Our approximation is definitely smaller than our prediction from virtual work, which we expected, but the difference is about a factor of 6. So now the question becomes, is our elastic curve going to be potentially 6 times greater than the prediction the elastic curve we get if we assumed point B as a perfectly fixed cantilever? And when I superimpose these two shapes, it doesn't seem unreasonable that we could get such a behavior. But if you're still not comfortable with a factor of 6 difference, you can use other methods to predict displacement. When we get to the stiffness method of structural analysis, we'll have yet another tool we could use to predict slope and predict displacement. But for now, I'm going to say that our prediction using virtual work is reasonable based on the comparison of these two elastic curves. Now what about our slope predictions? Our approximate prediction was a minus 34.1, and positive would have been a clockwise rotation or a rise in the slope. Kip feet squared over EI, and we said positive would look like that. And then we just saw above our prediction of a positive 162 kip feet squared over EI, where positive is in the opposite direction. So even though our signs are different, they both mean, because our sign conventions are opposite, that it's going in the same direction, that it does slope downward. Good, that's consistent with our drawn display shape or elastic curve. This approximation is supposed to be an underestimate, and it is smaller than the magnitude we predict with virtual work. Good. Our virtual work prediction is about 5 times larger than our approximation. But again, looking at the elastic curves compared between the two methods, it's not unreasonable to think that our slope at the end of the real structure would be 5 times bigger than the approximation. And we already saw a 6 times different here in the deflection, so that's fairly consistent. Again, I'm going to call this reasonable. But if you're not convinced, once we get to the stiffness method, you can check it with yet another method. Now let's go back and review the process we followed. We started by approximating our answers for vertical displacement and slope at point C, because we want to have something to help us evaluate the reasonableness of our virtual work predictions at the end. To do that, we used formulas from the front cover of our text. We were then ready to begin the virtual work process. We calculated moment equations in the two members of the frame due to real load. We then repeated the process for the virtual force. We have to apply a virtual force if we're looking for a real displacement. And notice that our coordinate system, x1 and x2, have to be consistent from the moment equations for the real loads and the moment equation for the virtual force. The m's have to be drawn the same way on our free body as well. We then took off the virtual force and applied the virtual moment so that we could generate the equations we'll need in order to predict slope at point C. Again, using the same x-coordinate systems and the same direction for moment on our free bodies, we obtain the virtual moment equations. We then multiplied the virtual moment times the real moment, divided by EI, integrate with respect to x over the length of each member, added those quantities up, and obtained our prediction of displacement, and then slope. And then we compared those results with our approximations. And since our approximations are to be lower bounds, we gained confidence seeing that they are smaller than the predictions from virtual work. And by comparing the elastic curves, the displaced shape drawings of the real structure and our approximate structure, we rationalized that the magnitude of difference between our prediction from virtual work and our approximation could be reasonable, and so we're going to say that we have reasonable predictions from virtual work. Well done.